So we're looking at a problem, the word problem. There's a lot going on in here, but basically, Armin is deciding, is he going to pay individually for games that he goes to, or is he going to buy a season pass for $175? Of course, you want to spend the least amount of money to be able to get this entertainment. So if you only go to one game, it would cost you $175 to go to one game if you get a season pass, whereas it would only cost you $14 if you went to one game. So obviously, if you're only planning on going to one game, buy a single ticket. But how many games would you need to go to in order for this to be more cost efficient to get the season pass? So let's figure that out. Got $15 per game times X number of games. And I want this total, remember that's $14 per game. I want that total to be greater than the cost of the flat fee of $175. And that's going to be the number of games where all of a sudden it's better to get the season pass. Okay, so I can, if that makes sense, as soon as I get to this value on the left is greater than 175, at that point, I should just get the season pass. So how many games would I need to go to, or would Armin need to go to? So at this point, we already have an inequality set up. I can just solve this. I'm going to divide both sides by 14. And you didn't have to set it up this way in order to get the answer. I imagine most people who got the correct answer didn't do it quite like this. But when I do this, I get 175 divided by 14, me 12.5. So I would need to go to more than 12.5 games. Armin would need to go to more than 12.5 games in order for the season pass to be more cost efficient. So that means 13 is the lowest number of games he'd need to go to. And that is the answer. And we can confirm that by just multiplying that out. I'm going to do 14 times 13. And what do I get? I get 182. So if he went to 13 games, he would be spending $182. At that point, it would have been better if he had got the season pass. There you go. Hopefully that's a problem that you're able to follow through and understand pretty well. All right, so we've got, let's see, we already did some ball work. So we're gonna look at functions, and this is gonna go back to Algebra 1, stuff you definitely did talk about last year. I know it's been a while since you would have talked about it, but still, we're gonna talk about functions. Think of the transformations that we're looking at as functions, and then the translations specifically. So let's start with this one. All right, so down below, we have a mix of these diagrams. They're called puddle diagrams. You might remember these from last year. And if you can remember what an algebraic function is, I'll go ahead and give you a little bit of a clue here that only one of these is not a function. And can you guys identify, anyone can do it, if anyone wants to circle which of these diagrams is showing something that is not a function? All right, so we have this one in the top right was circled first, and some of these are a little bit tricky. Pretty much, I'm sure everyone knows that this is a function. Even if you forgot what a function is, you're probably like, yeah, that one seems appropriate. And it is, that is a function. It is this one in the top right that is not a function. And here's where we want to remember what a function is. A function is defined where every input has only one output. So all three of these, this input right here only goes to that one output. This input right here only goes to that one output. Now notice we have two inputs both going to the same output, but that's okay. We can do that. In fact, in the next one, we have three different inputs only going to one output, and not all these outputs are used. That's fine. This is still a function. As long as every input has only one output, it is a function. This one, of course, the problem is that this one input goes to two different outputs, and that is not okay as far as functions go. You might have heard the analogy of a mail carrier delivering mail. And if you have a letter, that's your input. The mail can only go to one mailbox. It can't go to two different mailboxes. So you could have 3 letters go to the same mailbox, but you can't have 1 letter go to 2 different mailboxes. So if you think about that, if that analogy is helpful, that's something to think about for functions. Okay. So this just reiterates this point. I don't need to say too much more about it. So this one over here on the left is a function, but the one on the right is not. And -1 and 1 both go to 5, but that's fine because it's each one only has one output. This has 0 go to 2 different outputs, and that's not okay. So that's the problem with that one. Okay, so what I wanted to do is just give a little bit of practice with evaluating functions. So here's f of x, it equals 3x minus 8. And I want you guys there with some scratch paper that you should have available next to you all the time. I want you to evaluate this where x equals 3, and I want you to find f of 3 for that function. And I will pause, let you guys do that. As soon as you have an answer, anyone can feel free to write the answer on the screen. Okay, so here we have f of 3 equals 1, and that is correct. If it's been a while and you're not sure how we got that, let's see what happened. We did f of 3, which means I want to take 3 and plug it in anywhere I had this x before. I want to replace that with a 3. So now it's going to be 3 times 3 minus 8. And this becomes 3 times 3, of course, is 9 minus 8. 9 minus 8 is pretty straightforward. We get 1 out of that. So not much to this, but we are going to be doing something like this in a minute with some geometric transformations that will be a little bit new. So it's important to kind of understand the basics of functions to begin with. All right, let's do this one more time. Here's this function. It looks a little more complicated, but honestly, when you plug stuff in, it's not going to be that bad. I want you guys to find the value when x equals -4. In other words, f of -4. Now, you might not get it right, but I do encourage you to work on this and put your answer on the screen when you found it. Okay, very good. I got 4 different people. Go ahead, put answers up there. Thank you, everyone, for working through this, and thank you for working at home. Okay, and let's just double check to make sure that 6 is right. With this many people getting the same answer, I think it's right. All right, so the key thing with this, and if you didn't get it, here's one thing that you might be a little bit confused about. We're doing -4 plugged in everywhere we have an x. So what that means for the first term is going to be -4 in parentheses squared. All right, and then plus 3 times -4 and plus 2. So if I'm going through and solving this, I already know I'm going to have a plus 2 right here. I'm actually going to work right to left. 3 times -4. We have to remember when we multiply a positive times a negative, we actually end up with a negative product. So 3 times 4 is 12, but because it's a positive times a negative, it's going to be -12. So I'm just going to put -12 right here. Now this is where people might, and you might have screwed up there because it's easy to get confused with the positives and the negatives. Now the next one, if you did -4 squared, you're essentially saying -4 times -4, which is, and that's times right there, that's going to be +16 because your negatives actually cancel out. And the 4 times 4 is 16, but the negatives cancel each other out. So this should be +16. But here's what can happen. You have to be careful. If on your calculator, you just did -4 squared, what this is going to read it as is 4 squared and then a negative answer. So that's why it's important we have these parentheses. It's not negative and then in parentheses 4 squared. It's -4 and then square of that. So that could be where some people made mistakes. But anyways, if we go through and finish this, if you still have questions on that, you can stick around, we can go through it. 16 minus 12 is 4 plus 2, which is indeed the answer that we see on the screen. So very good, everybody. And thank you, everyone, for working on that. Even if you didn't get it right at home, hopefully you can see where you made your mistake. And if you didn't even try it at home, then you're not even going to know where you might have made a mistake. So that's why it's really important to try this stuff. Okay, one last thing about functions. There is a special type of function called a one-to-one function. This might be new for you. Maybe you did learn about it. It's not going to be that big of a deal. I doubt this will show up on the test, but it is important to talk about. So while every function has to have one output for every input, a one-to-one function has one input for every output. So it looks like this. So these other functions that we saw where we had three different inputs going to the same output, that is not one-to-one. It's basically saying that if A goes to I, then I goes to A, in reverse order. And there's only one input per output. And this means that if we have four inputs, we have to have the exact same number of outputs. So this right here, I'm just going to put dots to represent it. If that was my input and this is my output, I have, all these go into one output. It's not a function, or sorry, it is a function. It's not one-to-one because I have four inputs, but only one output. So there we go. Not too complicated with that. Pretty straightforward idea. And we're going to come right back to it when we start talking about geometric functions. But first, let me know you're here. So transformations as functions. When we perform a transformation, we are using a geometric function. So we're taking that same idea we talked about and we're going to use it here. Now, it actually, it's very nice that it kind of works like those same diagrams. We were drawing all these dots, and we're drawing them connecting over to different things over here. We have a very clear sort of visual on that. When we do this translation, this is a translation right here. So B is being translated over to B prime. So that is the input and the output. C is being translated over C prime. That's the input and the output. So we can actually see it just like those puddle diagrams. And of course, A is being translated over to A prime. And we have the input and the output. They're visual. It's not just numbers like in algebra. We actually have visuals on these and outputs. Okay, each input, each has only one output image point. And additionally, since each output has only one input, this is a one-to-one function. So a transformation can be defined one-to-one function on the coordinate plane. Okay, and I will just mention very briefly, if my internet is acting up and I'm like cutting in and out, if someone could just like message me to let me know that something's going on, because I wouldn't know. So hopefully that hasn't been happening. Okay, let's move ahead and look at this. So when we use algebraic functions like we just did, we have one input that was our f of x output. When we use geometric functions, our coordinates. So we're going to be getting a new coordinate as an output. We're going to say the coordinate for this point, I'm going to transformation to this point. What's my new point going to be? And so that's why I put x prime, y prime. So the name that we have for this is called a coordinate rule. Okay. All right, thanks for letting me know. So our coordinate rule, we're using 1, 2 as the input. And I want to input that into this coordinate rule. And so I'll use that language a lot, coordinate rule, but it is basically just a geometric function. All right. So I'm going to go ahead and do t of 1, 2. Now, just like before, when we took our x value and we plugged it in for x, we're going to do the same thing here, but now we have a y value also. So I'm going to take the y value and plug that in for y. And notice this comma right here. That means that we're creating a coordinate. We're going to have two different expressions to evaluate. We're going to have our x coordinate we need to solve for and our y coordinate. All right, so if I do this here, I will plug that in. And that's going to give me, this 1 getting plugged in is going to give me 1 plus 1. I'm just using that first expression here. And then I'm going to plug the 2 in for y right there. And that's going to give me 2 minus 4. So the calculations are pretty straightforward for this. I'm going to do the one on the left separately. So 1 plus 1 is 2. The one on the right I'll do separately. 2 minus 4 is -2. So what this tells me is that when I plug in 1, 2 as a coordinate into this coordinate rule, I'm going to get 2, -2 as my output. So on its own, it's pretty straightforward. Okay. And if there are any questions, you can have me come back to this or whatever you need. But I'm going to assume that everyone followed along, and we're going to look at these 3 coordinate rules. And these can look somewhat complicated. So I'll run through A with you and C. I'll let you guys do B on your own. But let's just I'll do this one more time. So first of all, I need to show you, we're going to be using the same input each time, 2, 4 as our input. And if that was a little bit confusing why I plugged the 2 in, remember your coordinates are X and Y. So this is my actual X equals 2 here and Y equals 4. So if that was not clear before, hopefully that makes a little more sense now. So if I do A of 2, 4, then what that's saying is I'm going to plug the X in right here. And that means 2 is going to get plugged in. I'm going to get 2 times 2 for the first coordinate. And then 4 gets plugged in right here. It's going to give me -4 plus 4. And the calculations really aren't too bad. When we get into our actual transformation functions, the calculations are never super complicated. So anyways, when I do this, it's going to be 2 times 2 is 4. -4 plus 4, well, what's that going to be?
Zero.
0, yeah. Again, working with positives and negatives and integers sometimes can cause a little confusion, but this is essentially, this could be arranged to say 4 minus 4 if we wanted to. So there we go. When I plug 2, 4 into this coordinate rule, I get 4, 0 out as my output. Okay. Go ahead and try B real quick, and I'll just show this. B of 2, 4. And you guys can work on that, and as soon as anyone has an answer, you can feel free to plug that in. All right, that is fantastic. We plugged in the 2 values. So now you can evaluate the X coordinate and the Y coordinate separately, and we can come up with the actual coordinates. So what is our X coordinate going to be? There we go. Thank you for writing that in, Atira. All right, you got it both. Thank you. Okay, very good. That is the answer, and you can actually see all the work right there. So if there's any confusion on that, again, just make sure you're sticking around after class. We can go and look over any of this stuff again. And I can make up some new coordinate rules until it sinks in. All right, now I wanted to go through C with you because this one looks a bit weird. First of all, it has, we're putting an exponent as the variable, so that's weird. But more importantly, the X value is not going to the first coordinate, but it's going to the second coordinate. And the Y is going to the first coordinate. And that can happen. In fact, we're going to see that when we get into our coordinate rules. And not today, but we're going to see that in the next few days. So let's kind of see what happens here. If I'm going to do C of 2, 4, then the X is going to get plugged in. And that's going to be, I'll just put 8 over something and then 4 raised to the power of something. So my 2 actually gets plugged in to 4 of X up here. So that's where the 2 goes. You can see where I plugged that in. And then it's going to be 4 over Y. And since my Y value is 4, remember, X equals 2, Y equals 4. I'm going to just put the 4 down here in the denominator. So calculations wise, it's not too bad, but we do have this weird looking coordinate rule. 8 divided by 4 is 2, 4 squared is 16, and there we go. So when you flip your coordinates, then you want to be on the lookout for that and make sure you're plugging it into the right spot. So it's just good to kind of think, okay, Y gets plugged in here, X gets, you can run through it. If there are any questions about this, again, I keep saying it, but I just want to make sure everyone hears it. If there are still questions about this, make sure you are asking those questions and not just forging ahead saying you'll figure it out later. Okay, so now we're kind of getting to the end of our lesson of the day. Now there was a lot of conceptual stuff that we've thrown out there, and we went through it somewhat quickly, but we're going to be focused on translation functions now, and this is the same example we saw before. So what of course you can see is happening is that every single point I'm going, looks like if I count that up, that's 5 to the right, so plus 5, and then 3 down, so that's -3. And every point is doing the same thing. All right, from your homework last night, you should have practiced with that already and feel comfortable with this idea. So every single one of these is moving with that movement, sorry, plus 5, -3. So what's essentially happening is that the X coordinate, I'm changing it by a factor of 5, not a factor of 5, but by a value of 5. And keep in mind, because your X coordinate, I'm going to draw an axis right here. This is your X right here. This is your Y. So if I'm going up or down, right or left, that's changing my, well, let's focus on the right and the left. If I'm going right, that's changing my X coordinate by a positive amount. If I go to the left, that's changing my X coordinate by a negative amount. And then with your Y value, up and down represent your positive and negative there. So here's what's essentially happening. I have some kind of an input coordinate X, and for every one of them, I'm adding 5 to it. So this is going to be X plus 5 for my for this translation. And then it's going to be whatever my starting Y coordinate is, it's going to be Y minus 3. And we don't have to end it right there. We can just double check that this coordinate rule is correct. All right, that seems correct to me, but we can double check it. And the way we do that is I'm going to start with this. It doesn't matter which one I pick, but I'm going to start with A. And this coordinate for A is -4, 1. So it's -4 in the X direction, 1 in the Y direction, up 1. So I'm going to just run this through the formula. So T of -4, 1 is going to give me -4 plus 5 and 1 minus 3. So when I do that again, it's going to give me -4 plus 5 is 1. 1 minus 3 is -2. So if my coordinate rule is correct, A prime should be at 1, -2. And now I can actually see that right here. And if I find the coordinates for that, that is at 1, -2. So I could confirm that with the other 2 points, but hopefully the point is clear and you guys are able to see that as well. So just to repeat myself another time, if it's not clear, let me know and we can come back to this. All right, so just to finish this up before we look at the Delta math, there's our generic formula for translation functions is right here. So we use the T so that we know it's a translation. And a translation of coordinate xy is going to be x plus h, y plus k. And h is going to represent how far we're moving in the x direction. K can represent how far we're moving in the y direction. But keep in mind, h and k can both be negative also. So if h is negative, that means we're moving to the left. If k is negative, that means we're moving down. Okay. I could repeat myself, but I'm going to assume everyone's following along. Okay, so I'm actually going to skip that. What I wanted to show you, we're going to have an assignment on Delta Math, and there's going to be, I wanted to show you on Canvas real quick that there are a couple of references for you, and then I'll show you Delta Math before you leave. So if I come over, I think that's Delta Math actually. Let's see. All right, let me go back to the main module. All right, so right up here at the very top for resources, this is nothing fancy, it's a coordinate plane. And this is exactly what you think it is. But if this is helpful, you can kind of copy, download this picture. You don't have to get this one, but bottom line, if you don't have graph paper at home and you want to mark using your iPad, annotate all over the screen using this can be very helpful. So of course, I encourage you to have some graph paper if that's an easier thing to do, but this is available. Maybe a lot of you never ever use it, but just know that it is available for you. The other thing is down at the very bottom here, I put this coordinate rule reference sheet. That's what you were looking at when we first came here. And what you can see are, we're going to be looking at reflection and rotation rules in the next few days. If you want to already look at those, you can, but that will make some sense in the few days. The translation rule is right here. So right here, it tells you that H represents your horizontal shift and K represents your vertical shift. And this will be a handy thing to have available when we get all of our coordinate rules. So right now, you don't need to worry about these, but as we kind of derive those rules later, this is a good reference to have available. Okay, so on Delta Math, you have two things to do tonight. One is translation of a point. And this is pretty straightforward. It gives you a point, it tells you to go left and up 4. Now you don't have to actually write out a coordinate rule in order to do this, but just to put this into perspective, we're essentially saying we do have this coordinate rule, T of XY, which means that left 3 is the same as going X minus 3, and up 4 is the same as Y plus 4. I want you to be comfortable with that notation. So now if I plug in 3, 3, or 3, negative 3, I'm sorry, then what that gives me is 3 minus 3 and negative 3 plus 4. So 3 minus 3 is going to be 0. Negative 3 plus 4 is going to be 1. So it shouldn't be complex as far as the calculations go. It's just going to be making sure you're doing the correct calculations. We'll double check that that's right. And we got the green check mark. And here's the nice thing. If you didn't get it right, it is going to show you your coordinate rule. It's going to show you what you should have done. And so you'll have a chance to correct yourself as you go through. So those are pretty straightforward compared to like when you think about what we did in class today. The other thing is variations on this. And this gets a little bit more complex, but it's really not that bad. Also, once you kind of work through one or two problems, the rest of them should fall into place. So here's my pre-image point. So I started here. It says the image of the point 8, 1, which means this is my input or the pre-image. The image of that translation is 9, 2. So what did I change? Well, I went from 8 to 9. So in the x direction, I added 1. And then I went from 1 to 2. So in the y direction, I also added 1. So it might be helpful here to actually write out your coordinate rule. And what that tells me is that I just did x plus 1 and y plus 1. And that was my coordinate rule for this. You're going to have to kind of do a little bit of reverse engineering. Look at these 2 points and figure out how they changed. Now I can do the same thing. And honestly, I probably don't need to write anything else out for this because my next point is 0.55. If all I'm doing is adding 1 to each, that's really simple. That's just going to be 6, 6. So I'll submit that, and I did it right. Notice it goes through, and it tells you how to derive this. So again, work those. I think you have 5 of each problem. I can't remember. And so that's it for your homework tonight. And at this point, if you have any questions, please feel free to stick around. If you are good to go, you feel like you understood everything, have a wonderful day, and I will see you tomorrow. Oh, last thing before you leave, if you don't have Delta Math, make sure you get taken care of so you can stick around to take care of that too. All right. Have a great day.